Hello. Okay. Okay. I can continue the virtualization topic. Uh, First, I'll introduce myself. My name is Changpeng Liu. I'm a storage software engineer from Intel. And this topic will continue the virtualization topic. And as you may know, at SPDK 1804 release, we released an experimental feature, vhost-NVMe, which can be used to accelerate the guest NVMe IO in NVMe interface. So currently, if you want to use the block device inside your guest VM, there are several kinds of interface you can use, right? Philip has mentioned that they use the Virtual SCSI in their guest VM. And also you can try Virtual block controllers inside your VM. And now we can provide another option with NVMe controllers in the guest VM. And currently, for the open source solution in the QEMU, there are two open source solutions for this part. The first one is the QEMU emulated NVMe device. It can use any file-based backend. And the second one is the QEMU NVMe block driver based on VFIO. This new solution provides QEMU to access physical NVMe controller in user space. But this solution has one pitfall. That means it can be only accessed, the physical NVMe can only be accessed by one QEMU instance. And okay, for the NVMe benefits, I listed several and here. Maybe this is not important because the NVMe is fast and designed for the SSDs. The first one is multi-queue support, and it can integrate with Linux generic block driver directly. And the second one is fast data path. This can be compared with the Virtual SCSI solution because there are no SCSI middle layer driver involved for this data path. And the third one is it defines the whole bunch of the command sets which can support the discard and write zeros commands. Okay, here is the SPV host target summary. And currently we can support the three different interfaces in the guest VM. The first one is the Virtual SCSI, and the second one is the Virtual block. And of course, the third one is the NVMe controllers. For the SPV host target, we have three virtual controllers inside our vhost target. Virtual SCSI controllers, virtual block controllers, and also virtual NVMe controllers. And all those three different controllers are built on top of abstract block device in SPDK. For the QEMU part, you can see there are two yellow drivers. It's already in the QEMU Git repository. And for this green vhost-NVMe driver, currently we maintain a separate patch in the SP Garrett Hub. So users may ask why we can integrate Virtual and NVMe into a single target because Virtual protocol and NVMe protocol has much in similar. Let's see. Both Virtual and the NVMe protocol use the RAM-based data structures. You can see that for the Virtual protocol, there are two available RAMs for submission for request, and use the range for the responses. And for the NVMe part, they use the submission queue and completion queue. Also, there are indexes for both of the two data structures to indicate which entry has the latest request or response. Here I'll give an example to talk about the vhost-user and the NVMe protocol format. Let's assume we have just one request, and this request has only one data segment. For the vhost-user protocol, it must use the 3 descriptors. The first one points to the SCSI request. Most likely, the request will occupy 62 bytes. And the next descriptor will point to the data buffer. And the third one will point to the SCSI response. So for this request, it will occupy, you can see, 16 bytes for the descriptors. And we have 3 descriptors plus the SCSI request, SCSI response, and the data buffer itself. For the NVMe part, NVMe request has a fixed 64 bytes, and it has internal field which can point to the data buffer. NVMe response has fixed 16 bytes. So for this request, it will occupy NVMe request plus data plus response. So from here, we can see that NVMe protocol, at least is more efficient than the vhost-user. Here I listed the vhost diagram. For the vhost-SCSI and vhost-user solutions, they use the shared virtual RAMs between the QEMU and the SPDK host. And for this vhost-NVMe solution, it's shared IOQ pairs from the QEMU and the SPDK host. So they are both use similar mechanisms. You can see that for the event FD, it can be used to inject the IOQ into the guest to notify that the IO is completed. The Unix domain socket, it just used to set up the shared RAMs between the guest and the QEMU. Between the QEMU and the SPDK host. It is not used for the data path. Okay, implementation here. For the SPDK host NVMe target, we maintain a virtualized NVMe controller inside our target. And below this target, each virtual NVMe controller is assigned with a polar. So this is the IOQ polar. And each NVMe can be composed by one namespace or several namespaces, depending on user configuration. And the IOQ pairs is shared between the guest and SPDK host target. So let's see a detailed example to show how the IO is executed between these two parts. First, the guest will submit a request to the submission queue. Then, SPDK will pick up this new request from the submission queue. And it will submit to the backend. After the IO is completed, it will post a response to the completion queue, and it will inject the interrupt to the guest. After the guest is interrupted, it will poll the completion queue to get this response. This is the whole part for the IO execution. Here I raised the 2 questions here about this IO execution. Well, the first one is how the IOQ pairs can be shared between the guest and SPDK host target. The second one is that how the SPDK can know which entry has this new request. next. Here is the example to answer the first question. Create the IO submission queue. Guest will send the create IO submission queue. This is the queue. This is the command of create submission queue. PRP1 here. PRP1 is a 64-bit memory address which point to the IO submission, which point to the submission queue's memory address. If this runs in the guest VM, so this is the guest physical memory address. Guest will submit this command to admin queue and ring the doorbell, write the doorbell to let the QEMU know that a new request occurs. QEMU will pick up this admin command. Currently, QEMU did not process such command. It just forwarded to SPDK via the Unix domain socket. After SP received this command, it will pick up this request and paste the PRP1 in this command. So it will do a simple memory translation to translate from the guest physical memory address to virtual host memory address. So after this step, both the guest and the SPK can see this IO submission queue now. Okay, another question, how SP knows which entry of this submission queue has the new request, right? Okay, when the guest send a new request to the submission queue, then it needed to write the schedule, the doorbell to let the controller know which entry has this new request. For physical NVMe devices, this register is located at the PCI bus base. So when this run in the guest VM, each write of to the doorbell will trigger MMR writes, which will cause the VM exit event. This VM exit event will impact the performance a lot. So NVMe 1.3 specification released a new feature, optional admin command support for doorbell buffer config. It used for emulated NVMe controllers. Guest can update this scheduled doorbell buff instead of submission queue's doorbell registers. So with this new feature, each submission will write the scheduled doorbell. So for the submission pass, there is no MMR writes happen with this feature. Okay, this is the scheduled doorbell buffer. Actually, it is two separate 4 kilobytes data buffers inside the guest VM. Guest will send this command to SPDK. After the SP receives this command, it will start the poller to pull this scheduled doorbell. Here is the benchmarks collected for this new solution. For the purpose to evaluate the efficiency of CPU utilization and some key VM events, so this example I just started one VM with one NVMe SD than 28. You can see that from the left part for the RPS part, vhost-NVMe, and vhost SCSI and vhost block. This is 3 vhost solutions. And the yellow one is the QEMU NVMe for the use the kernel NVMe drivers. And for the CPU utilization part, you can see that from this, at least for this three vhost solutions, the CPU utilization, we cannot see too much difference from each other. But from the key VM event, you can see for the QEMU part, there are so many key VM MMR writes and also so many QEMU exit events happen for this solution. Another one is another test cases with this solution. I studied 8 VMs with 4 NVMe SSDs. Here, just collect the 3 vhost solutions. The first one is vhost SCSI and vhost block, and the last one is vhost-NVMe. You can see that for the RPS part, higher is better. Vhost-NVMe will increase 20% compared with the vhost SCSI solution. And for the latent part, vhost-NVMe can decrease about 26 for the latency. Some future work about this feature, interrupt collapsing. If you are familiar with Linux NVMe driver in the kernel space, you will find that when submit a new request to a submission queue, each submission will, the kernel NVMe driver will pull this submission, will pull the completion queue first before each submission new request. So with this feature, we can do some interrupt collapsing because actually the kernel space Linux driver do not need so many QEMU events to interrupt it that the I/O is finished. So with this feature, we can improve this the performance with many more VMs. And the second one is the admin command. Currently, admin command is processed as the QEMU driver. We want to move this admin command into the SPV host target user, so that for the QEMU driver, we can just maintain a very small patch. All the admin commands and IO commands are processed as SPK. The third one is the migration support and upstreaming to QEMU host driver. Because currently we maintain a separate patch in the SPK GitHub, and if we can prove that, or actually we have proved that it's more efficient, we can send this patch to the QEMU community to upstream to the QEMU Git repository. And the last one is, as I just mentioned, because this feature is heavily depends on the NVMe 1.3 new feature. With this new feature, Linux kernel 4.12 just added this support with 4.12. So currently, it can only be used with the newer kernel than 4.12. Okay, that's all for my part. Any questions?
Question over here, 1 sec.
Thank you. So I saw that there's efforts to bring admin commands as well into vhost. What is the impact of not doing that? What's the, is it add significant latency or?
You mean VM exit?
So in your future, the last slide you had.
Okay.
Yeah, you talked about admin commands also being serviced at the vhost. So without doing that, what
yeah,
impact?
I get it. Because for this part, actually, that's because for the currently Linux kernel driver, it only put the IO queues into consideration. Although the spec defines both for admin queue and IO queues, but for the implicit part, Linux kernel driver did not take the admin queue into consideration. So for the first days, I put the admin queue commands into the QEMU part. But for the future, I think we can optimize this.
Right. I understand that would be a good optimization, but without doing that, would that cause an impact in latency for the other IOs?
You mean this future work to the performance or latency impact?
Right. I mean, generally, admin commands don't happen that often after it's initialized, right?
Yeah.
You'll do it for maybe looking at smart or something like that. But, you know, occasionally, you know, in temperature and stuff like that. So occasionally you may have to do that. But my worries or my curiosity is, without doing this, would it impact the general I/O that's running under vhost?
Actually, no impact to the I/O part.
Okay.
Yeah.
So it's just more of a clearing
More,
up the organizational.
Yes.
Okay.
More optimization work.
Okay. Thank you.
Yeah.
Hi, one more question here. So if I understand it right, so each I/O queue and admin queue of the NVMe device is shared by both kernel and SPDK. So the kernel code paths come from QEMU. Is it right?
Yes. Currently, if it's just for the I/O queues, because the admin queue for this part in the Linux kernel driver, it is still needed to write the scheduled, write the doorbell registers.
Sorry, so what you were saying is the admin queue cannot be shared by SPDK at present.
Yes, currently, yes. But the spec define this feature not only for the IQ, but also include the admin queue. But from the implementation now, they just implemented the IQ.
Okay, so for admin commands, if the user space has to pass the admin commands to kernel, does it cause a performance bottleneck?
Yes, if you if for your use depends on the user scenarios. I think for most users they will not send too many admin commands while using this NVMe SD, right?
Yeah, that's true.
So this will impact the performance, but not too much.
Okay, thank you.
Yeah.
Any other questions? Okay. Thanks, Chong Pong.
Thank you.